Hello everyone, this is Doug, and in this video we're going to talk about attractive forces. Attractive forces are a super important, very fundamental concept in chemistry. Attractive forces are what describe why some things are solids and some things are gases. It describes why some things are soluble in water and some things aren't. They're very important. So we're going to do two videos on this. In this first video we're just going to talk about what are the attractive forces and kind of go through the various ones that there are, like hydrogen bonding or ion-ion or something like that. So if you remember from a previous video I did when we were talking about the differences between solids and liquids and gases, we talked about how solids have really slow particle speeds, but gases have very fast ones, or that the solids are typically more dense and gases are typically the least dense. And then we ended that by saying, right, that the amount of attraction between the particles differed between the different phases. That solids, if you looked at solids, they looked very sticky. They looked like they had very strong attractions to one another, right? If you go back and you look at that video again, you'll remember that solids had particles that were very closely and tightly held together, that those particles did not slip and slide all over each other. Unlike liquids, right, which still were attracted to each other, those particles still held together, but there was a little bit less of a connection, and you could see those particles slip and slide across one another and rearrange themselves. And then we saw that with gases, right, there were no attraction whatsoever. Those particles in a gas phase were just flying around, bouncing off of each other, but they weren't aggregating, they weren't clumping together. They showed no signs of attraction whatsoever. So it's for these reasons that we need to talk about these attractive forces, right? And so attractive forces is a kind of a more modern term. When I learned chemistry, everyone would talk about intermolecular forces, and I'll talk about that in a second. But attractive forces is just really supposed to broaden the umbrella of the types of ways that any two particles could be attracted. And so the big five are the ion-ion attractive force, the ion-dipole attractive force, hydrogen bonding, dipole-dipoles, and then the dispersion forces or London dispersion forces. We'll go through all of these in a lot more detail here in a second, but I just want to point out that these bottom three, numbers 3, 4, and 5, these are what used to be called intermolecular forces. So intermolecular forces, or IMFs, intermolecular forces. Now, because this has the word molecular in them, this only applies to covalent compounds, which we'll see in a second is why only these bottom three could be considered intermolecular forces, right? Because in ion-ion and ion-dipole, ions are not molecules, so hence you can't apply the term intermolecular force to them. So attractive forces just allows you to talk about all of these different attractions and not just ones involving covalent compounds. So if you're watching this and you've heard of intermolecular forces before, we're basically talking about the same thing, but just plus more forces is the idea. So let's take a look at a couple of examples and start talking about what these attractive forces look like. So for my first example, I have Epsom salts, magnesium sulfate. This is, a lot of you probably have heard of Epsom salts. This would be like what you would put in a bath if you had sore muscles or something like that. Athletes use it. If you just want to relax, people use it. But it's a solid. It's just a solid white crystalline material. And if you look at the formula, right, we've got something from the far left, magnesium, and we've got sulfur and oxygen from the far right, oxygen. So those are much more electronegative. So we have a large difference in electronegativity, which means that this compound must be ionic. And if you don't remember how to identify if a compound is ionic, polar covalent, or nonpolar covalent, this would be a good time to stop watching this video and go back and watch your types of compounds videos again, because it'll be important to you need to be able to identify the type of compound in order to identify the attractive force that it has. So Epsom salts are solid. It's an ionic compound. So if I draw out Epsom salts, right, I know that if it's ionic, that means that all of these are individual particles. So I've got a magnesium ion, a sulfate ion, a magnesium ion, and I'll just draw a few of these. But right, again, imagine that this is in the trillions of billions, numbers that you can't really, we don't have words for it, right? It's just so many if you had a single crystal of magnesium sulfate. And we drew this before, back when we were talking about ionic bonds and ionic compounds, and we alternated them before, right? Because we said, well, the positive magnesiums can be attracted to the negative sulfate, and this negative sulfates can be attracted to that positive magnesium. That positive magnesiums can be attracted to that negative sulfate, and so on and so forth. And so what we see, right, are all of these little attractions. These little green lines that I'm drawing are just supposed to be attractions between oppositely charged things, right? So they're opposite charges, so there's attraction to one another. So we have here, right, so this is just an electromagnetic attraction. Electromagnetic magnetic attraction, which probably you've all heard, right? You've all heard that like charges repel and opposite charges attract. So here we have something that's positive being attracted to something that's negative, right? They attract one another. That's the only thing that's really going on with ions. They're just little tiny, tiny, tiny magnets. One's positive, one's negative, so they're attracted to one another. But when they're ions, when you have that sort of attraction, that's what we call, right, this attraction, that's what we call the ion attractive force. Right, because you're having two things that are ions attracting one another. They have full charges. In my case, I have plus 2s and minus 2s, so there's even more attraction. But you have full charges, and so between two things that are ions. So it's one ion and another ion. So hence the term ion-ion. And I know it sounds like I'm just kind of repeating myself or stuttering, but we'll see in a second that it's important that you say what both particles are. This ion-ion attractive force also, right, this is also known as an ionic bond. So they're the same thing. An ionic bond is an ion-ion attractive force. It's the same thing. It's the attraction between two oppositely charged particles. And that's it. And so we've seen this drawing before. Ion-ion attractive force is just between two things that are ions. Now if I move to a compound that's wildly different, right, so here I have water. We've all experienced water, right? It's a liquid at normal temperatures and pressures. If we look at water, I'll draw one out in case you're not remembering what water looks like. So if we have a water molecule, it is covalent compound because I've got the lines drawn on it. That means it's covalent, plus both of them have a small difference in electronegativity, right? Oxygen and hydrogen have a small difference in electronegativity, which means that it's a polar covalent molecule. So polar covalent. Let me try that again. Polar covalent. And if it's polar covalent, right, then that must mean I need to put my partial charges on here again, right? So I've got my partially negative oxygen, partially positive hydrogen. I've got polar bonds here. And remember, right, that whichever element is more electronegative, that's the element that you're going to give the partial negative to. And so now my question is, if I have two of these water molecules, right, I'll draw a second one, I'll put the charges on it. If I have a second water molecule here, how might these two water molecules be attracted to one another, right? Up above we said that, well, of course, the magnesium that's positive is going to be attracted to the sulfates that are negative. And this is really the same question up here, right? So if my water molecule, if I ask myself, well, what part of this water molecule, if this water molecule's hydrogen was going to be attracted to any part of this other water molecule, the partially positive hydrogen should be attracted to the negative of the other molecule, the negative oxygen of the other molecule. And so what you see is these water molecules kind of line up so that those opposite charges attract, just kind of like we saw up above with the sodium sulfate. They're going to line up in a relatively ordered way to get as many of those attractions going on as possible. So I'm going to put a whole bunch of partial negative, partial positive, partial positive. I'll put in all these partial charges here so that we can see just how these all end up lining up, right? And I'll draw again in green just like I did above. This partially positive hydrogen is going to be attracted to that partially negative O. This partially positive hydrogen is attracted to that negatively charged O. This hydrogen to that O, this hydrogen to that O. And so you get these attractions that are different than the ion-ion attraction because these aren't ions, right? They're not full charges. These are just partial charges. And in fact, they're charges that occurred because you have a polar molecule, because you have a dipole. And so since you have a dipole, right, I'll draw in a dipole arrow. Since you have a dipole, the idea is that this is called the dipole-dipole attractive force. Dipole-dipole attractive force. Right, because the two participants in this attraction here, each of them have a dipole. One has a dipole, the other one has a dipole. They both have dipoles. And so that's different, right? Ion-ion attractive force, we had a full charge attracted to another full charge. Here we have a partial charge being attracted to another partial charge. So they're not full charges. So they're going to be inherently weaker, right? The larger the charge, the more attraction. The smaller the charge, the less attraction. So there's a very big difference between our ion-ion and our dipole-dipole. Ion-ion are for ionic compounds. Dipole-dipoles are for polar compounds, things that have dipoles. Let's look at a few more examples. Now if I look at ammonia, ammonia is also a polar compound. I'll draw an ammonia molecule or two here. So I've got ammonia, so NH3. If I look at ammonia, same thing, right? Hydrogen is less electronegative than nitrogen, so it gets the partial positive. Nitrogen gets the negative, and then all the other hydrogens get positives also. So if I'm drawing a second nitrogen molecule, it looks like the hydrogen should be attracted to the other one's nitrogen. Oops. And we can just go on and on and on. I won't draw a billion molecules here, but just enough to kind of make the point that, again, what we see is that these partial charges end up aligning. Right? So you definitely want to make sure that you're able to draw these partial charges on these molecules so that you can figure out how things are going to line up. So that partially positive hydrogen is attracted to that nitrogen, that partially positive hydrogen is attracted to that nitrogen. And again, these are just attractions. They're just little magnets. They're not actually like bonds or anything like that. Not in the traditional sense of like a covalent bond. And so we see the same thing. We have two polar molecules being attracted to one another. So this would be another example of a dipole-dipole attraction. Another dipole-dipole, right? All of these would be dipole-dipole attractive forces. Now, if I look at acetone here, acetone may not be as familiar to you. This is the component in like nail polish remover, excuse me. But it's also a polar molecule. It's also a polar compound. I'll draw out some acetone molecules for you here. So C double bond O. We've got a CH3 and a CH3. So it's a ketone. And if I look at the polar bonds for this one, I have a negative oxygen and a partially positive carbon. And so, of course, it makes sense that if I was to draw a second acetone, its oxygen would be attracted to the other one's carbon, because, again, those are the things that have opposite charges. And you could just go on and on. Again, I will stop after 3 molecules. But I just want to show you one more example of how these charges end up aligning. And so again, I'm going to draw partial charges between my partially positive carbon and my partially negative O, partially positive carbon, partially negative O. And this is another example, right, of two things that are polar, so they're going to have these dipole-dipole attractions. So dipole, dipole. Now this is the point where I need to mention hydrogen bonding, because hydrogen bonding is just a special kind of dipole-dipole. Hydrogen bonding is a dipole-dipole attractive force, but it has its own special name because hydrogen bonds are the strongest type of dipole-dipole. So I'm going to draw a little line here. And so we have hydrogen bonding. I'm putting it in quotes here. The idea is that hydrogen bonding is just it's just the strongest type of dipole attractive force. But it is a dipole-dipole, and it has its own special name. And the thing with hydrogen bonding is that you need to have a hydrogen on one of the very electronegative elements. So we've got fluorine is the most electronegative element. Oxygen is up there, and then nitrogen is up there also. These are very, very electronegative elements. And since they're so electronegative, that means that these partial charges are pretty big, right? So the partial negative on the O or the N. Sorry, these are not whole molecules. I'm just drawing the hydrogen attached to one of those atoms. So you got to have an H on one of those elements, and then they need to in turn be attracted to one of those elements. So F or O or N on some other molecule. So they need to be attracted to one of those other elements, which again, because they're so electronegative, those things are probably going to be negative in whatever molecule they're in. And so it's this attraction between these two components that gives you what's called a hydrogen bond. This would be considered the hydrogen bond. So hydrogen bond here. So again, the big key players is that you've got to have an F or an O or an N. That's what's most important. And then they also have to be attracted to an F or an O or an N, right? So it's a hydrogen on one of those. I don't like that it's called a hydrogen bond, because then students think that it's a bond, like a covalent bond. It is just an attraction. It is just an attractive force, just like dipole-dipole, just like ion-ion. There's just that you have two oppositely charged things attracted to one another. So if I go back and I look at my examples, I got ammonia and acetone here, right? Since hydrogen bonding is a type of dipole-dipole, anytime I think I have a dipole-dipole, I just want to double check to see if it is that hydrogen bonding type or just a regular type. And so if I look up here for my ammonia, it looks like that what I've got, I'll draw this out like this. It looks like what I've got, right, with ammonia, I do have a hydrogen on a nitrogen, just like it said, right, just like we said here. And I also do have that it's attracted to a nitrogen, which is what we said here. So that would make this, in fact, a hydrogen bond, right? Because I have an N on an H, and it's attracted to an N, that makes it a hydrogen bond. So yes, it's a dipole-dipole, but specifically a hydrogen bond. Which again is just like the strongest type. It's just a really strong type of dipole-dipole. If I go down to the one below, my partial positive here is actually not even on a hydrogen, it's on a carbon. So that means I'm dead in the water. I mean, I need a hydrogen that's positive, not a carbon that's positive. Yes, it's being attracted to an O, which would be helpful, but I'm missing this. This is no good. So this is not a hydrogen. Since this is not H+, this is not hydrogen bonding. It's not going to be an H bond, which means it's just a regular type of dipole-dipole. It's just a standard dipole-dipole attraction. So hydrogen bonding is just that kind of stronger type, and you have to have an H on one of those elements. Fluorine, oxygen, nitrogen. So let's do two more here, and then we'll kind of summarize these. If you have oxygen, right, we know oxygen is a gas. We know oxygen's a gas. And if you take a look at oxygen, if you look at an oxygen molecule, you have an O double bonded to an O. Which means, right, that must mean we have a nonpolar compound. So this is nonpolar covalent. Nonpolar covalent compound, because neither of those oxygens is more electronegative than the other one, so they share electrons equally. And if I draw a second oxygen molecule, let's just say over here, if I want to know what sort of attractive force there is, I don't really see much going on here, right? It's not ionic, so there's no full charges. It's not a dipole. It doesn't have a dipole, so there's no partial charges. It's got nothing. It's got nothing going on. There's no reason for there to be an attraction. So it's just not much of an attraction. Now, where this kind of gets trickier is if you put this under a lot of pressure and you really cool down the temperature, you can get them to stick, but it takes a little doing. And so let's imagine for a second that these are whizzing around and that they're flying around and they're going to go get close to each other. And let's see what happens there. All right, so I'm going to redraw these oxygens. So here's one O2. Here's another O2. I'm trying to draw them much closer together. And what I'm going to do is I'm going to draw the electron clouds, right? So before, the idea was that their electron clouds were supposed to be pretty evenly distributed, because again, it's a nonpolar compound. So imagine that these electron clouds are nice and even. Now, if I bring them together, those electron clouds are going to repel each other. So as I bring the O2 down below here, and I bring it closer to the O2 up above, its electron cloud is going to be repelled by the other one's electron cloud. And so what you're going to see is this deformed electron cloud. It's no longer going to be even. It's going to be lopsided, right? Because the electrons from the bottom one are going to repel the electrons on the top one. So they're going to try to move away from the other O2 molecule. But in doing so, what happens is that now there are more electrons on the top half of this molecule than there are on the bottom half. And since electrons are negative, that means that this top half of the molecule is getting a little negative because it's getting kind of more electron density than it normally would. In turn, the bottom half of the molecule is getting a little less electron density, so that's getting a little positive because, again, the electrons which are negative are moving away from that area. And so you set up this sort of lopsided electron cloud, or what's called an instantaneous dipole, or a momentary dipole. Just for a moment, those electrons flop over to the other side of the molecule. But if they do that, the O2 molecule on the bottom, its electron cloud also deforms. And in this case, since there's little positives on the bottom, those electrons are going to shy to the top, be attracted to that, which makes the top of this molecule a little negative, and the bottom of this molecule a little positive. And what you'll notice here, right, is I've set up positives. So I have positive charges and negative charges set up next to each other. And so we get an attraction between the partially positive bottom of the top one and the partially negative top of the bottom one. And this is what we call the dispersion forces, or the instantaneous dipoles. So this is what we call a dispersion force, or London dispersion force. It's also known, like I was saying, as an instantaneous dipole. It only lasts for a second. Because under normal temperatures and pressures, right, the idea is that this is so weak. This is very, very weak. I'll write weak here. It's so weak that the oxygen molecules are easily able to just kind of bounce off of each other and break those dispersion forces, right? So all of the oxygen molecules that are in the air right now that we're breathing, yes, they bang into each other. Yes, they might even exhibit like a dispersion force for a tiny bit, but it's so warm in our atmosphere and in our rooms and in our bodies that the idea is that that's plenty of energy for them to just bounce right back off. Not a problem. You can't liquefy oxygen until you get super, super cold and you increase the pressures a lot. So you got to get super, super, super cold in order to make it so that they don't have enough energy to bounce off each other anymore, so that they just stick. But that's what the dispersion force is. If I did the same example with butane here, so butane also it's mostly a gas at room temperature. It's just about boils at room temperature. But it's also nonpolar because it's only C's and H's. It's also nonpolar. So if we look at butane, it's going to be the same thing, CH3, CH2, CH2, CH3. If I bring two of those molecules together, we get the same effect. So CH3, CH2. And we can get that same sort of lopsided electron cloud situation that we had below, or that we had above with the O2s. And so a lot of partially positive bottom part here, partially negative top part here. Just put in all these dipoles for you. And now though, if you look at this, since this molecule is bigger, there's a lot more surface area to it. And since there's more surface area, there's more places for attractions. So larger surface area. So if you have a larger surface area, that means more attraction. Because there's simply just a larger surface, right? It's like having like a little piece of Velcro versus having a big piece of Velcro, right? The bigger the piece of Velcro, the more stuck together everything can be. And so what we tend to see with these dispersion forces is that they increase with the size of the molecule. So they increase with the size of the molecule. So when you get like giant molecules, they can actually be solid-ish, like waxes are a good example of some that basically just has dispersion forces, but they're so big that they actually stay together and don't fly around as gases. So the dispersion force is just this instantaneous dipole. It's really weak. Everything has a dispersion force. It's just that all the things that aren't nonpolar have a better one. And so that describes their behavior better. So that is, I know that was a long video. Hopefully you made it through the whole thing. But those are the different attractive forces. We'll talk more about ion-dipole in the next video. But I've arranged these for you in order of strongest to weakest, right? So your number one, these are all your strongest. Ion, right? Because ion had like the full charges, right? You had things that have full charges. We'll see that ion-dipole will be the next one because you have a full charge with a partial charge. Hydrogen bonding is a type of dipole-dipole, right? So you have partial charges on both, right? Those are both dipole-dipole. So I'll even write that here. I'll emphasize it again. Both are dipole-dipole. And then lastly, we have the London dispersion forces, which is just the nonpolar things. So there's just no charges really to talk about whatsoever, just the instantaneous ones. And so what we'll do, and like we said, those are the weakest. And so what we'll do in the next video is we'll take all of this knowledge that we just got and we'll apply it to some questions, and we'll identify some attractive forces in different interactions so that we can see how this relates to things like melting point and boiling point, things like that. So anyways, if you have any questions or comments, go ahead and leave them down below. Happy studying, and get ready to watch that next video.